today's lecture is from Luc Darmé at EP2I in Lyon, France, giving us a lecture about Feebly Interacting Particles. Luc is now a postdoc fellow from Marie Curie funding in France, and he's been working in Italy and also in Warsaw for the last years. And he's giving us the honors to tell us about his research. So thanks a lot, Luc. I know it's a lot of work to prepare those lectures, and everything is in your hands. So
okay. Okay, thanks a lot, Sharam. It's not just an honor. I mean, it's a pleasure talking about such nice physics around. So today, today on Fridays, we'll try to have 2 lectures on that, which should roughly be around like 4 hours-ish, depending on how many questions and how motivated we are. So for today's lecture, I'll try to make at least 1 break in the middle so that you can grab a coffee or something. So thanks a lot for the GGI and for Sharam for organizing everything. What we're going to talk today is about kind of finding the invisible. So how can we look for and actually describe, theoretically speaking, objects which are both very light, but also completely hidden, meaning that they are beyond the standard model particles that somehow we missed before because they were too light. So, okay, this is going to be the first, the plan of the first lecture. So I'm going to have a mixture of some slides, and in some cases, when I really want to delve a bit more into some of the building and some of the theory, I'll actually write down directly on the tablet. So I hope this works down. So be prepared in case you want to take notes that we'll be writing down at one point. So, okay, we'll start quite slowly, I would say, because fortunately we have time. The idea is that I just very slowly introduce what we mean by this concept, which is kind of a very big umbrella of feebly interacting particle, which is basically just a name, which covers roughly everything which is both light and very feebly interacting, hence the name. The second part, which will take us quite a lot of time, I'll try to show you examples on how we can actually construct ourselves feebly interacting particle models. So of course, I mean, you want to be able to construct that in a fully consistent scenario and setup, consistent with the standard model, this kind of structures and this kind of objects. So we'll see and look a bit at how we can build this kind of objects using what is typically called the portal operator idea. Okay, and in the last part of this first lecture, we'll try to see very briefly what is a parameter space for looking at these types of objects, and we'll do that mostly in colliders in the first time. So the idea is that in this first lecture, we cover most of the theory around this kind of objects, some of the very basics limits, so that you can familiarize yourself with the types of objects we can have, the couplings, the interactions they have with the standard model. And then in a second lecture, we'll delve a bit more into the phenomenology of those objects and some current hot topics, so delving about dark matter or G-2, for instance. But first things first, we need to see like what are in the hell are these feebly interacting particles objects. So for that, I would suggest that we take like a step back, and by step, I mean a big step, meaning we come back 1 century ago. We're in the 30s. In the 30s, we've more or less at the very dawn of particle physics, we've understood that you have an electron which can get out of some nuclei during disintegration. We call that beta decay. Now, beta decay has a pretty annoying feature, I would say, was this following, that if you would look at the decay of a cobalt nuclei, for instance, into an Ni, you would expect to see an E-. This is what they called at the time beta disintegration, so beta decay. So you just emit an electrons. This, of course, comes from a weak current, as we'll come back in a second. The issue is the following. This process has to proceed just to preserve a lepton number via the emission of both an electrons and a neutrino. So I mean, at the fundamental level, what they could not see was that we're transforming a neutron into a proton via a weak current, and so therefore we're emitting a pair of leptons, one a charged lepton and the other being the neutrino. But now, if you're a physicist, is basically you don't have access to that. You don't have access to that because the only part that you know is something that is either charged, which is what you prefer because it's very easy to see in your spectrometer, or something that at least deposits some energy, so like some nuclei, for instance. The neutrinos are unknown, and so this will lead you to a world of problem for the simple reason that if you look at something which is a two-body decay, you expect a very peculiar energy distribution. You expect a line. So this line should be somewhere around here, this transition energy. Instead, what they were seeing with this very smooth spectrum that, of course, nowadays you can reconstruct just from the three-body decay theory. But if you don't know about neutrinos, which they did not, energy conservation appeared broken. Instead of having this energy there, you somehow lack a lot of energy. And worse than that, you're actually having a distribution of objects so that you're not very predictive on the actual energy that your electron has. So these neutrinos were in fact the first truly dark particle. I mean, they had no idea about weak interaction. They just knew about somehow the nuclear interactions and electromagnetism. So comes Pauli's intuition about what is widely recognized as being a bit the insight toward what is called neutrinos, and it's a pretty famous letter from the 1930s called Dear Radioactive Ladies and Gentlemen. So, I mean, this letter is absolutely wonderful. So you see that Pauli wrote to some people in the Congress and basically tells us that he had an idea for these wrong statistics of the weak decays. His desperate remedy, as he called it, is to try to postulate that they exist in the nuclei electrically neutral particle, which he wanted to call neutrons. What is funny there is that he was thinking about neutrinos because he was looking for this particle, something which would escape the nucleus at the same time as the electrons. And somehow he called it neutrons, which they do it in neutral particles, which we do call neutrons. But those are not the ones which are the reason we can actually call this particle neutrinos. So they looked like the neutron of Pauli, but of course they are not. What is wonderful is just based on the distribution that we've seen before, it's able to put a first limit on what should be the mass of the neutrino, and they basically claim that it should not be too much below the proton mass. This is simply because if that's the case, then you see this distribution will be changed and skewed a bit. So, I mean, the most incredible things of all, I think, is that Pauli was not actually there. And so it was indispensable here in Zurich because, you know, you had a ball. So somehow police did not actually go to the Congress and just discover the neutrino by sending a letter, all the while attending a ball somewhere in the night. So that was another time. So if we advance a bit more, what do we know? Well, we're in a situation where we know that this interaction that Pauli was looking after is the weak interactions. So these neutrinos, they were completely dark particle, but of course, I mean, we know that they are nonetheless quite feebly interacting at low energy because of the exchange of an electroweak boson. I'm not telling you anything new here. You can just look, for instance, at the decay of a muon via the exchange of a W bosons. Now, of course, the idea of Fermi was that if the W was very massive, you could just integrate out and create 4 Fermi operators, which is called now the Fermi operator, this one here, both to describe, for instance, the decay of neutrons or the decay of muons in that case. Now, what is wonderful here is that this Fermi constant is actually a very good benchmark of what we could call hidden or not. Basically, it sets what is the interaction, what are the interactions for neutrinos. Neutrinos, we've seen quite a lot of those, but as you very well know, they still interact quite feebly. And so therefore, it's very good to have this benchmark in mind. So the Fermi interaction was, of course, given by just integrating out this particle. So the mass here is the W mass. The coupling is the weak interactions. And so altogether, you get something which is of the order of 10 to the minus 5 GeV minus 2. So notice the GeV minus 2 because that's a dimension 6 interaction there. So if you plot everything together there, it really gives you that if you want to have something hidden, there is 2 possibilities. One is the one of Fermi, mainly telling you that the mediator is super heavy and you don't have access to this object, and because it's so heavy, it suppresses the interaction. The other possibility, which of course is not the one used in nature for the Fermi interaction that could be used per se, is if this coupling, this G square here, is very small. As you can see, there was 2 possibilities there to get this 10 to the minus 5. Either I take this guy around 10 to the minus 6 and a mediator at the GeV scale, or I go back to the Fermi theory. This tells you that you can try to decompose the entire world of the known particle into a very broad and schematic plane of mass versus coupling. So in this x-axis here, you have the mass of the objects that we have. So you see that I'm spanning all the way from the electron volt up to the GeV, and here it's the coupling. So when you go down, your particle becomes darker and darker, basically harder to see. So if you're around the GeV, you're within the realm of LHC and what we usually colloquially call the energy frontier of particle physics. So what is hard here is not really it's hard to get these particles because they're so massive, so tiny if you want, that it's very hard to get the energy to produce them in the first place. But you don't have to stop there. You can also go down a bit and go around the GeV scale. Around the GeV scale, we have plenty of machines nowadays and even before, which could look for a particle of this mass. So if you want to make sure that you've never seen these objects before, you have to ensure that the coupling that they have with the standard model is tiny. So if you go back to that thing, you need to ensure that instead, if M is small, then G has to be even smaller so that you will hide those objects. So typically you have a first threshold there, which occurs around Meson's factory. So count between 5 to 10 GeV. We'll come back to that. And this occurs also around the B Meson mass, because once you reach the realm of Meson decay, you'll be able to use those to test for light objects. And we'll come back to that quite extensively in the following. If you still go down, you reach another very interesting region, which I would call beam dumps. So beam dumps are another types of accelerator experiments. In fact, the very first type of accelerator experiments that we had at our disposal. Instead of colliding two particles with the same energy, you just accelerate one beam of particle and you hit a target. But because of that, the center of mass energy which is available for producing new objects only goes as a square root of the energy times the mass of the target. Typically, if you hit a proton, it means that you have square root of proton mass times energy, which means that it's very hard to basically reach largely above the GeV with these types of particles. You pay a heavy price because of the square roots. And this is why we move to colliders. If you go even lower in mass, meaning that you reach below the MeV, then you basically get out from the accelerator domain and enter what I would call the astrophysics part. There are several reasons for that, but the two main ones are that below the MeV, you're below the electron mass. So typically you have particles which cannot decay into electrons anymore, so they are very quickly very stable. On top of that, if you remember your primordial universe, the MeV is also roughly where the neutrinos start decoupling. This is all where we know very well the evolution of the universe, because this is where we have the nucleosynthesis, the primordial nucleosynthesis. So this is where we start knowing a lot from the cosmology, and also we have some supernova data sets here. If you go even lower, basically below the GeV, then you reach star temperatures. And it means that now you have very large and very big ovens in the sky that you can use to bake those particles out. And because stars are hugely massive, you can use these huge ovens to produce a lot of those objects. And so if you want to hide them, you have to get couplings which are even smaller. So you see that you have always this kind of triangle there. And as a guideline, which will be all revealed in lecture 2, I put something called this diagonal of freeze outline. So we'll calculate that in the second lecture. It just tells you a bit that we have good reasons to not only look for this part of the spectrum, but also go down into this region here. And in fact, I mean, I could have continued the dark matter line all the way up to the microelectron volts and the axions. Okay, so you see that basically we have a whole world of experiments to draw for, and we have to study a bit each in different turns because they draw in totally and entirely different physics there. So in this lecture, I will tend to focus a bit more when I delve about phenomenology and this region here, basically down to the GeV all the way up to the TeV. And so I will just leave aside a bit what I would call ultralight particles, like for instance axions, just because the phenomenology is a bit different on those kinds of objects, and we have only 4 hours to use. So, where we know? Well, we fast forward a century, and then we can ask, okay, why did we want actually to look at that? So if you come back to this picture that I had before, after the discovery of the neutrino, we pushed toward all the way up to the top at the neutron. And then we were wondering about getting SUSY, something that did not occur. Then we were wondering about getting extra dimension or new particles above the TeV, which still we did not solve. So of course you have the question there, am I really wanting to look for new physics here, meaning in the very massive regime? Or maybe it's useful to look if I actually missed something before, meaning that I have to turn back and look there. So this brings the first question on the theory side, and which one that we want to describe more properly, which is, how can you really hide something that is so light? So you've seen basically throughout times, we really went through all of those particles one by one. We built the electrons, discovered the muons, and build bigger and bigger colliders so that we could get all of those particles, the quark, the tau out. So if we want to hide something, we have to make sure as a very first step that it does not interact with any of the known force, because this is how we discovered leptons, for instance. So we have to produce an object which is a singlet under the full gauge group of the standard model. So is it something that is crazy? Not really, in fact, because if you actually look at the standard model itself, you'll figure out that, well, the gauge groups also act differently on all of the various particles. For instance, if we look at right-handed particles there, they don't fight SU2 at all. SU2 weak at all. Similarly, of course, if you look at leptons, they will not interact into the SU3 of color. And in fact, I mean, I've ordered all those nice particles in such a way that we see the missing gap there. even the star model, if you just follow through and putting something more left-right symmetrics, you'd like to introduce the particles right under neutrinos, which in fact won't interact neither under SU2 left, nor into SUY, and neither into the color SU3. So altogether, we have quite a lot of reasons to believe that it would be possible to have particles beyond the standard models, which simply would not interact with any of the gauge groups that we have already, meaning that they would be extremely hard to see, because those gauge groups are the way and the means that we have of testing and looking for new objects. So having an object which is, let's say, not interacting in any of the gauge group of the standard model is the very first step into hiding an object. So this really brings us, I would say, toward the paradigm for Feebly interacting particles. So FIPs are really this kind of new, if I were trying to get a definition, fitting a bit everything, those are this new neutral particle that would interact with the standard model via very suppressed new interactions. And I mean, we have different reasons. Objects that I've listed there, from the hierarchy program to the neutrino mass to the nature of dark matter, and we actually cover quite a few of those. All of those reasons basically give you candidates from axions, light dark matter, dark photon, dark Higgses. Those are all objects that you've probably a bit heard about before already. What is fascinating is that not only are we good reasons to look at them from the theory side, on the experimental side, we have a plethora of experiments to look for those objects. This covers flavor experiments like Bell2, Na62, dark matter experiments, of course, but also neutrino detectors. And even at the LHC, you can have a big and interesting programs trying to look for those types of objects, in particular regarding what is called the long-lived particle program. There's a whole program that will be developed at LHC, for instance, phaser, with the idea of producing particles at the interaction point and observing them 100 meters away. So Feebly interacting particles are really at the very sweet crossroad between having a nice theoretical description and being extremely easy to look for, or at least being easy to look for in a huge variety of experiments, basically. Okay, so this is more for the less introduction. So now we actually do some hard work to actually create those objects. So as I advertised to you at that stage, the idea is that you want to create Feebly interacting particle interaction with the standard model by having objects which are completely neutral or singlets under the standard gauge groups. So that means that if you have a neutral particles, it must be coupled to a neutral current in the standard model. So I'm this fashion there, a part of standard model and another part of new physics. We're building our own portal models out of that. I do that. Did you have any questions on what we had before we proceed? It was just pretty generic as an introduction. So, okay, there we go. I suggest we start building our portal model. So let me just put that here so that you actually have somewhere on your screen, these charges, because those are the charges in the standard model. So we actually need those objects when we try to construct that. Okay, so normally you are able to see the tablet here. Yes. Okay, can you just confirm that you can read what I'm writing here?
Yeah, good. Perfect.
Okay, very good. So the first step we're going to do is try to build this portal operator that we have before. So we're looking to produce terms in Lagrangian that will have some dependence of this way, x minus n, and then I'm putting some portal operator here. This portal operator will be constructed from standard model fields and interactions, and then I have to put something like a new physics interaction here. So m dimension, and so of course we will be first rested into looking at operators which have the lowest dimension, at least those which are renormalizable, because we expect those to be dominant in a new physics theory. So how do we do? And of course, lambda is a UV scale. And this is a UV scale. The first one we may want to look for is, well, maybe the simplest one. And I'll do the first one and then I'll try to look for the others. So this one is called the Higgs portal. It's arguably one of the simplest because it has basically no structure at all. The idea is that we'll look for something like this, which has both an H and an H dagger. Now, of course, this is a Higgs here, it's a scalar field. This is literally the mass term in the standard model Lagrangian, and we can do that because, well, we can contract those two objects, they have opposites, all the opposite charges. And so this is very well motivated. Additionally, you'll see that there's a dimension 2, so a pretty relevant operator altogether. So on top of that, we'll notice that the Lorentz structure, those object is trivially a Lorentz scalar. So you can basically put anything nearby those objects without any constraint on the Lorentz structure. So the simplest, let's say, dark operator, so new physics operator, I can add on that. Is something like a dark Higgs. In fact, I just constructed an operator by constructing two complex scalars together. So I can do exactly the same thing for the dark sector operator. So I'll write this one and call it SS dagger. Oops, with S, the complex. Choose whichever scalar you want. So based on these two objects, of course, the full Lagrangian I can try to construct is something. We'll have an interaction. Oops, let's write. We'll have a term which is usually called a mixing term, a quadratic mixing term between these two objects. This is literally the operator I wrote to you before. And the second term I could use, for instance, is a trilinear. So I could have something like that, H dagger, and then I have an S, and I need to add a Hermitian conjugate. So what will this operator do after electroweak symmetry breaking? So to simplicity, we'll just set right now lambda s at 0, or assume that it's tiny enough that it's not that of an issue. Well, once you actually set the Higgs into its VEV, you'll get something as a square root of 1 and then d. That the previous interaction I showed you will actually transform into a mixing mass term. So my Lagrangian now includes something like an interaction between the S. So this is my effective mass square for the mixing, and then I have HS plus some Hermitian conjugates. That implies that on the mass squared of those objects, you'll have something like that, eventually, mass of the Higgs, then the mixing coefficients I just had, and then some MS. Up to numerical factors depending on what you choose, and if you went for a complex scalar or a real scalar for the dark Higgs. What's very important, of course, here is that if you're in the situation where VAS is much smaller than MH squared, something that you typically expect. And on top of that, well, you want a light dark Higgs. After all, we're trying to build light objects. So you want also this MS squared to be much smaller than MH squared. So if you add these two things together, the main effect will be to create a small mixing theta between the Higgs and the dark Higgs. So we can very easily estimate those things by just diagonalizing the above mass matrix, and it comes out proportional to, of course, the tiny coefficient that we have here, which is all in the limits when this is approximately 0 and MS much smaller than MH. What does that mean? Well, we literally just constructed a scenario in which, using in my Lagrangian something called a portal operator, I was able to link the standard model to some dark light objects. So in practice, it means that, for instance, if I want to look at the decay of an S, it will be able to mix with some mixing of theta, go into an off-shell Higgs, and then decay into, let's say, a pair of standard model fermions proportional to the Yukawa couplings of these fermions. So you see that the mixing here is actually providing me with an effective portal in the low energy theory, telling me that if I have this kind of objects, they will be very light and interact just like a Higgs with a small theta, which depends on the parameter of my full theory, which basically means that it's a full free parameter from the Fino perspective. Okay, so you see that this is basically the first portal we could think of, and it's arguably also one of the simplest one, because it's very easy to construct in the first place. Okay, so now we'll actually move to a second portal. So I'll just give you the name. It's called vector portal. So does anyone knows actually which one is this one? Not all sleeping already. Any idea? Come on. Let's try to look a bit at the quantum numbers of those objects here, right? So we just used the fact that this was 1, 2, 1/2. So SU3, SU2, and 1/2. Now we try to see if we can construct another one. So of course you see that we can do quite a lot with all those. Well, all those bosonic objects are not perfect. except for the B, right? The B, which is the object from an abelian gauge group, says, of course, no charge neither under net U3, by design neither under net U2. And because it's an abelian gauge group, it does not make any self-interaction if you want. So this is actually interesting to look in practice. The reason is the following. If you look at something that I'll call B mu nu, which is literally the gauge field strength of the hypercharge, so it will read like that. For an abelian gauge group, this object is also a gauge invariant. Because remember, the transformation normally should proceed in non-abelian gauge groups with some the structure constant of my SUN, let's say. But for U1, you have known. So B is a gauge invariant. Which was basically what we needed to fit the bill of creating a portal operator. Now you'll notice directly that it's a bit different from my previous objects, right? Because even though it's a full gauge invariant, it's pretty clear that it has Lorentz indices. I mean, it's a Lorentz tensor. So it has a non-trivial Lorentz structure. So from my definition of portal operator, that's absolutely not an issue. I mean, you can just look at those objects and it's a gauge singlet, so it fits the bill. What it tells us, it's also a Lorentz structure. So what it tells us nonetheless is that if we want to add something to create a term in the Lagrangian, so if we want to create an interaction term in my Lagrangian, something like that, what do I have to do? Well, I have to do first, let's say, putting my B mu nu, and then because this is a Lorentz tensor, I have to put it with something that is also a Lorentz tensor. So what about something like V mu nu? After all, this is not mentioned 4, so I'll just decide that I put an epsilon and I put what, something like a 2 cosinus theta w, where theta w is a Weinberg angle for a reason which will become clear instantaneously. So what is this V mu nu? Well, it has to be a tensor under Lorentz. So the simplest case is to introduce what I would call the dark photon, V mu, which is just basically a massive abelian gauge bosons. So this way I can define V mu nu as being equal literally to d mu V nu minus d nu V mu. And therefore I've written another interaction between those two objects here. Now at that stage you should be slightly worried about the terms that I've written in the Lagrangian, right? I mean, this is not at all like the previous contribution I've written, which was a mass mixing term. This is a mixing in the kinetic terms, which means that my particles are not well normalized. So basically, I don't have a good definition of what is a photon and what is this dark photon anymore, simply because those are not canonically normalized objects. So what you need to do at that stage is two things. The first thing is that, first of all, we may go down to the low scale, because most of the time what we're really interested in is not the mixing with the hypercharged gauge boson, but rather with the photon eventually. So this Lagrangian will become something like epsilon divided by 2, and now I put F mu nu V mu nu. Is F mu nu the electromagnetic field strength. So if you write these things, you're still in a position where, well, those two objects are non-canonically normalized. So the simplest way of actually removing this term and coming back to Lagrangian, where the kinetic terms are normalized, is to replace and make a field redefinition. So basically, I'm going to take my photon, A0 mu, and then I'm going to take my dark photon, V mu, and then I'm going to make sure that they are transformed into new definition, A mu minus epsilon V mu, and then V mu. Oops, this is plus O of epsilon squared. So what I'm doing here is basically taking the photon and removing a small component of V mu, and you'll notice that this transformation is not symmetric, meaning that I don't take the dark photon and put a fraction of the photon in it. So this is completely on design. This is fully required by the masslessness, let's say, masslessness of the photon. So basically, you can actually check and you can use that on exercise. You can try to redefine this transformation by adding, for instance, a rotation, something that will preserve the diagonal kinetic term that we've produced from this transformation. and see that actually there is only one type of transformation to actually preserve the fact that the photon is massless. If you don't use this transformation in the fields, it's not an issue. You just redefine your fields. But you're in a very weird situation when you have two massive bosons, and the combination of these two, one of those guys is actually massless, which is of course absolutely not what you want. It makes the whole calculation extremely hard. This is actually exactly the same issue that what you maybe know from the renormalization of the photon and the Z boson. So when you actually calculate the photon and the Z renormalization groups, check. So let me first put this aside, that this is with MA equals 0. Okay. So this should kind of find, so this entire constraint here may seem a bit strange. Like after all, what did I do? I just put my Lagrangian, added in the Lagrangian a contribution which made the kinetic term not fully normalized. And then I say to you, oh, but we can just redefine my gauge fields so that this term vanishes. And I'm left with something which is back in the diagonal and some interactions term, because of course you see that now I've put into my original photons pixel small components of dark photon, which means that now I have a new interactions, which comes from this tiny mixing epsilon there, which is roughly given by minus E times epsilon times V mu, and then I have the electromagnetic current. Oops. So this is the electromagnetic current. Oops. Okay, so this is where we wanted to finish if you want. But in a way, we could have started from it, which would have said, oh, look, I'm introducing a new object. It couples just like the hypercharge, but it has a much smaller coupling constant. And in fact, we'll find some of objects later on in the course called light vector bosons, in which we could actually put new, let's say, objects, which would interact directly at tree level with standard model particles. So the reason we've proceeded into this way is basically due to the original intuition of gamma Z mixing. So we may know in the standard model we have a very similar situation to this one, in the sense that we have already the presence of both neutral massive boson and a massless boson. Those are the photon and the Z. The issue is that you may write at tree level something like that. A0 has a loop here. For instance, you can put electrons in this loop, and then so at loop level, this contribution gives you something in the mixing self-energy for those two objects. So in fact, in order to construct a full theory, even in the standard model, once you want to go at one loop, you have to acknowledge the fact that your gauge bosons are mixing, and so therefore you have to design a proper renormalization procedure. So in fact, it's pretty easy to see that this kind of self-energy is directly linked to epsilon. In fact, epsilon is linked to this, this is gamma Z, and epsilon is in fact sigma gamma V divided by MV. Square here. So this is something that you can actually build directly from constructing your full theory, in which you have two objects which do not mix and are canonically normalized, but some interact with the same sets of fermions, and so therefore they renormalize and start mixing via these loops. What is very important is that as a conclusion, we expect this epsilon to be of one loop factor, so you know something like 1/16 pi square times sub log contribution, which comes from the loop here. So this epsilon, and this is why we use this parametrization, expect it to be a small parameter, and in a full UV theory, it should come naturally as soon as you have fermions which will interact into both the electroweak gauge groups and the new abelian gauge groups that I've put together. So this is a bit, this is a first example on how we can go from the UV theory and then use it as an effective theory in the low energy part in the low energy physics we're interested in the first place. So basically what this means is that eventually, after all these things, we're left with what? So a dark photon, after all these, let's say, changes, is simply what? It's a massive vector object, massive vector, and it has an interaction proportional to the electromagnetic one. Oops. but with a tiny coupling epsilon. So this is proportional to G electromagnetic. Sorry. This is proportional to G electromagnetic mu times epsilon. So again, this interaction is times epsilon. So basically it means that you can always construct something like that as vertices. The V will interact with anything that a photon would interact with, for instance, a pair of V plus E minus, but it would do so with a suppression epsilon. That, as we've seen, is typically given at least by a loop factor and maybe some additional suppressions. So basically we're talking about a tiny parameter of the order 10 to the minus 3-ish, which will be on top of that proportional to the electric charge. So you have to add 0.3. So this is something that is quite suppressed as an interaction. Okay, so I already gave you two portals. Does anyone have an idea of the next portal? So this one I can give you the actual dimension. This is a portal of dimension 5 halves. Any idea? Sarah, do you have an idea? Oh, I see that Aldo is here. Aldo, do you have an idea of the next portal in dimensions?
I was...
Very well. So dimension 5 half, what do we have? Well, I mean, the dimension kind of give it a bit away, right? You're in a situation when you have a half. So a half means that you're going to put fermions doublets in these objects in the first place. So dimension 5 halves is what we call the neutrino portal for a very simple reason. You could see it from there, right? You see that the lepton doublet is a 1, then a doublet and a -1/2. This is more or less what you need for Higgs right here. So in practice, I can write the terms in my Lagrangian, which would have a L bar. So I would have to interact it not with the Higgs, but with the so-called X tilde. Remember, this X tilde is defined precisely as being I sigma 2 times H dagger, which is of course the same thing if you want to write it in AJ, so using SU2 flavor indices, the same thing as this guy. Here we go. So this is an interesting beast, right? Because as you see, it's a Lorentz, of course. The Lorentz spinor is in dimension 5 half. This basically almost cry out to be built together with a dark fermion. So we've seen before in the Higgs portal, I've put a dark Higgs, so dark scalar. In the vector portal, I tended to put a dark vector in it. And so in this neutrino portal, basically what I want to put in is a fermion, a dark fermion in that. So the interaction, sorry, this is the ups O neutrino. So this is the operator itself. And so from this operator, what I want to introduce is something that would be, let's say, a sterile neutrino object, for instance. So is a fermionic gauge singlet. Okay. Now, this should ring a lot of bells at that stage, right? I mean, a fermionic gauge singlet, that's something that we've literally encountered 2 slides ago, a bit more, 3 slides ago here. This is exactly what we're lacking to kind of complete and make the standard left-right symmetric. On top of that, as you surely know, this is also what we lack to create a contribution as the neutrino mass terms. So in fact, this neutrino portal is extremely close by in link at the origin to what is called the type 1 CISO model, meaning that my full Lagrangian at that stage is given by this term. So you'll have the interaction here. I have a tiny Yukawa coupling, because this is exactly what it is. You interact with the Higgs, and you put an N here. Now notice that this is a fermionic gauge singlet, so it means that in principle, I can very easily create for it some kind of Majorana mass term, which would read like that. This is in Dirac for Fermi notations. And again, this is precisely what you'll expect for right-handed neutrinos, because if they have a large mass, then this implies that the neutrino mass matrix would follow in the very easy structure, which is 0v, vy, vy, and mn. This is so, right? Because in this mass matrix here, you'll have to get one eigenvalue of the mass mn, and the light eigenvalue, which will be the one, let's say, of the neutrinos, will be typically proportional to the square of the off-diagonal contribution, vy squared, divided by the mass of mn. Now, at that stage, you have two possibilities, right? If you really want to make this right-handed neutrino light objects, then you have to take it somewhere around the GV. So if you want that n is a feebly interacting particle, then typically we don't like those objects to be at the 10 to the 10, right? They're impossible to fit there. So we want to be a physics unit, for instance, we have Mn at least 10 of smaller than something like 10 GeV, so that we're a bit below the electroweak scale and self into the regime of these types of low energy physics. Of course, these are a strong implication, right? Because it means that if you want mu to be somewhere around the electron volt, then you have a situation where this implies it has to be somewhere below 10 to the minus 7, 10 to the minus 6, which is extremely small. So basically, we hit the first issue here. I want to construct something that is fully consistent and that will mixes and create to me, for instance, here the neutrino mass. And then I see that if I make prediction, well, we're completely out of reach of most of the current experimental searches. Fortunately, this is just a toy model. So this is for the seesaw mechanism. And as you know, probably there is plenty of fishes in the sea and many models to get the neutrino mass out of this kind of strategies, I would say. And so different, let's say different seesaw mechanisms who may lead to a different relationship between the coupling, Y, and the mass of the neutrino, or the mass of the right-handed neutrino, to a different relations between Y and Mn. So what we'll do is something that you typically want to do when you're in the bottom-up approach. So the pheno-driven, you said, okay, I have many different models from the top-down perspectives. Really, the simplest model gives me like one line, a prediction. So what I'm going to do is just break the relationship between these two objects. Basically, I'm going to tell, no, I have both free parameters. The first free parameter is the mass of the sterile neutrino. And the second free parameter is the angle, the mixing angle that it's going to have with the visible neutrino. So of course, if you're in a very precise seesaw model, these two objects will be linked by relationships like this one. But in principle, given that you don't know which seesaw model nature has chosen, you may not know for sure which actual relationship you have to take for. So therefore, from the bottom-up approach, define from the start something that is called a heavy neutral leptons, or HNL. So you've surely heard about that before. And a bit like we did for the dark photon, we'll just define those objects as being new light fermions, massive with a mass which is a free parameter, which are on top of that mixing with the standard model neutrinos, with an angle that is a parameter, a free parameter of your theories. And of course, you have three generations, so you can typically write theta E, theta nu, and theta nu. So exactly like the dark X, we're in a situation where now we've introduced a new light object, and the main way of actually seeing this object is because it has a tiny mixing with a standard model field. So for instance, this triggers something like that. You could look at the muon decay that we've looked for the Fermi constant. You have a muon, it emits a W that go by, for instance, into a muon and nu. Oh, but now you can say, oh, wait, I have a new particle which mixes with a neutrino. So I could also construct something like this. Instead of decaying into two neutrinos and a lepton, I know decaying into a lepton, a neutrino, and the sterile heavy neutrino object that I just interact. And the price I'm going to pay for that is, well, a small angle theta. Let's say if this is neutrino, so that will be some interaction, for instance, with the muon. And so if we do that, this means that this whole interaction is not proportional to the Fermi constant times a small suppression angle, right? So this is exactly more or less what I've advertised for you at the very beginning. This is like taking the Fermi interaction and suppressing it just a bit so that we are below what was the interaction for neutrinos. Okay, so we've actually worked quite a lot by that stage. So you see that we're able to construct a Higgs portal, a vector portal, and finally we've constructed these neutrino portals. Now, you've noticed that I've done everything by dimension. So I started by dimension 2 operators. Now I've moved to dimension 5 halves. So of course, there are higher dimensional operators. I mean, you can construct a full tower of those portal operators. I'll just mention before moving to the rest of this lecture is the one that you could construct even arguably one of the around, except from the Higgs. We could do exactly the same as what we did for the Higgs. Take an object and just basically square it. So for instance, we could construct what is called a fermionic portal operator, which could be just, let's say, one quark, a gamma mu, and another quark. That will also work. After all, I'm just taking two fermions. So those are dimension 3. So you'll notice that depending on what you put here, so I could use this one, but I could also have written, I don't know. So this is a PL. I could have put a gamma 5, or I could have gone instead for something a bit more exotic, like some interactions with only the right-handed objects, for instance, like gamma plus dr bar, gamma mu dr, and so on and so forth. You see that at that stage, you can start adding a lot of operators. And just like in the SMEFT, if you actually start moving higher and higher dimension, you start creating way more operators in your theory. And so the description starts getting less and less attractive in the first place. So what we can do for this ring is that this is the first steps. So you'll notice that this is dimension 3. So some of those objects you can construct types of things. I'll just like flash them out. One is so-called the ALP portal for axion-like particles. And it's a higher dimension 5 portals. And it looks like this. You have something, for instance, E gamma 5E, and then you have ME divided by lambda, and then you put an ALP. So this is because at the low energy theory, it looks like that. It could also have interaction with F mu nu. So here I put a tilde because this is the epsilon suppressed tensor interactions divided by lambda. Or you can just have, you could just go on like this. You can have what we call the fermion portal, which simply has like something like that. I gamma mu chi, so this is dimension 6, and so on and so forth. So of course, as I said, once you start reaching into higher dimension, this formalism starts losing its predictivity. So just like the SMEFT, you don't want to go to dimension 8 because, well, there you have millions of operators you want to look for. And on top of that, you know that they are all suppressed by some UV scales, here lambda, and so you expect them to be more and more irrelevant the higher you go in dimensions. Okay, so let me see. Doing the break now or a bit later? Well, maybe let's just try to summarize before moving to the break what we've seen so far. So this was really the introductory part of these lectures. And so basically what we've constructed so far are these portal interactions. So we've seen that basically it was simplest to basically match something in the Standard Model, which was a gauge singlet, to another object in the dark sector, which was also a dark singlet. So from there, we could construct different types of objects, right? We could construct the scalar port, putting a dark Higgs, and the main signature was mixing with the Standard Model Higgs. We could do the same for the vector portal, putting a dark photon in so that it would mix with a photon. And then I showed you the neutrino portals with heavy neutral leptons, and then even higher, you could move to dimension 3. So this is, of course, this is a bit on the theory side, the main tools that we'll have at our disposal. Of course, it's not all at the electroweak scale. We are theorists, so we want to be able to treat problems at different scales smoothly. The first thing we want to treat is the fact that, well, in principle, we may have both some effective theory below the GeV. So for instance, instead of having quarks, I have mesons there. I have only electrons, photons, and maybe neutrinos, neutrinos and maybe interaction with my Feebly Interacting Particle. The portal operators I've written to you were all written at the electroweak scale. And in principle, on the UV theory side, you may want to actually define a new UV theory which predicts this particle. So we need to develop also the tools on the theory side to be able to match those 3 scales. So from the bottom-up approach, there's an experimentalist which comes to you and said, oh, I want a particle which interacts only with electrons, for instance. Well, you have to be able to tell him, okay, that implies that your particle is going to interact, for instance, with left-handed leptons, and so therefore it should also have some interaction with the neutrinos, which may give you other constraints. You may also want to be able to match effective interaction with the mesons with the constituent quark interactions. And you also want to describe properly the renormalization group evolution, because if you define your theory at the electroweak scale and want to look at phenomena which occurs around the GeV scale, you may generate from the RG and from the flavor violation in the Standard Model additional flavor violating descriptions. Interactions which may be super constraining. So this part of the to-do list that we have to do a theory is to describe properly these kind of problems. We can also do the same thing from the top-down approach, meaning that we can start on the UV theory and then we may wonder, can I actually end up having one of the portal operator I showed you before. And there, everything is a bit reversed, right? If I introduce a new U1 gauge groups, I have to make sure that I'm treating it properly, that I don't introduce anomalies. I have also to make sure that I'm integrating heavy states. I have to make also sure, this seems a bit stupid, but this is often the case, that in my full theory, the main constraint actually do not come from my TV particles. So for instance, at the LH, I could maybe produce on shell some of the particles of my full theory, and this will be the dominant constraint, not the constraint on the light degrees of freedom of my theory. So a bit of a two that as a theorist, when you tackle those kind of issues, you have to take into account. So this means very practically that you have to match the different scales one to the other. So let's do it very briefly. For instance, if you go from the electroweak descriptions there, so those two here are fermion portal that have bundled together two fermions. Of course, once you move to the low energy theory, you can state with the chiral states. You have to go into the Dirac fermion that describes the standard model. So if you generate neutrinos and some gamma mu gamma 5 matrices, if you have some interaction with the neutrino portals I showed you before, you may generate mostly neutrino mixing, but also some additional operators here because of the exchange of the Higgs. And then you have to do the same thing for all of the operators that you have. If you start by quarks, then you have to do two things, right? The thing is matching the chiral states to the low energy ones. And the second thing is actually matching those low energy states, which are of course quarks, so either within baryons or mesons. So you have to describe those currents of quarks in terms of the meson. So using, for instance, chiral perturbation theory, if you want to play more with vector, you can use this terminal vector meson dominance, or just factorization of the amplitudes in the simplest case that you have available. So if we have some time later in this lecture or next time, we'll study just very briefly one of these links into the simplest case when you can just factorize the amplitudes. The last part of the operators that we've seen were bosonic ones, and those are a bit more complex because you see that you start producing a lot of operators from one operator in the UV. So if you look, for instance, at the Higgs portal, we've seen that the main effect was to have a mixing with the standard Higgs, which means that you naturally have interaction with all the fermions of the standard model, so the E, the U, the D, and some flavor violation as well. So, okay, and then you can do the same thing, for instance, for the out portals. So these two scales means that you have to be slightly careful from the very simple, let's say, portal description I showed you into getting the actual pheno right. You have to take care that you take all these steps properly so that you don't miss one part of the phenomenology along the way. Okay, so in the 5 minutes before we actually go into a break, I'll just want to speak to you about like some very peculiar detail case, which are some kind of funny theory. The first thing is what I call new light gauge bosons. So you may wonder something. In fact, you know that I showed you, I always write to you, let's say, take this portal operator, add another dark object, put these two together, and you get an interaction. In fact, our way of actually creating a new interaction is really to create a new interaction, just like we have in the standard model, basically adding a gauge groups. And so there's a question which is almost century old, which is not century, I'm exaggerating a bit, but decades old, which is what can we add to the standard model as a new gauge interactions? So it turns out that if you are not willing to add anything to the standard model, if you're not able to put, let's say, right on the neutrinos, for instance, then the anomaly cancellation, and okay, here is not the place to discuss at length the anomalies, but basically it's the idea that you want your quantum theory to be fully consistent and the calculation at one loop not to break your gauge symmetry. So, okay, you can check your favorite QFT books for that. But the main issue here is that, well, if you add an abelian gauge group, for instance, you have plenty of anomalies to take care of. You have the mixed anomaly with hypercharge, these two ones here, the third, the fully dark anomaly, and then you have the mixed anomaly with the normal gauge groups and the gravitational waves one. What was realized quite early on is that staggeringly, if you actually put all this together, the study is roughly complete in the sense that you cannot add any new symmetry with the only exception of the mu minus L tau, meaning that you make the lepton number a gauge interaction, and you make sure that opposite generation have opposite charges. So the most famous of those objects is mu minus L tau. So if you do that, then actually you find out that you have a completely anomaly-free theory. So you could add, with no cost to the standard model, those objects. Of course, it means that you interact a new force, and so you have to hide it by making tiny couplings. But in practice, nothing really changed afterwards. If you're willing to do a bit, Okay, I'm going to add some new fermions in my theory. So you basically said that just like heavy neutral leptons, I'm tolerating the fact that in my theory, I can put new fermionic gauge singlets. So particles which will not interact with any other standard gauge groups and only be charged under these new abelian gauge groups. So if you're willing to do so, then you go from 3 to infinity, basically. So there's been a whole industry of papers recently trying to figure out a bit what are the lists of those types of objects. And it turns out that if you're ready to tolerate different charges per generation, and for instance, take integer charges between -10 and 10, then you have something over 20 million solutions, which is quite a lot. But at the same time, it's not that much, because as I stressed here, it's only 1 in a billion, which is actually working from the solution of those equations here. But still, nonetheless, quite a lot. So it means that if you're willing to include, let's say, a new sterile particle, something that you may want to do, because, well, this is a Feebly interacting particle after significantly more choices. For instance, the most famous example is B minus L. So you charge the baryon number minus the lepton number, and this is anomaly free if you just add right not the neutrinos. But you could also add be a bit more exotic. For instance, charge it only under the third generation. It would work exactly the same. So this is a very funny case because, in fact, even if you introduce this particle, so this is a way of basically putting new interaction in the standard model from the top-down perspective. From the bottom-up perspective, it's quite dangerous to do so for a very simple reason. If you add a vector interaction with the standard model, then the interacting contribution will follow something like that. So you see the interaction Lagrangian is proportional to V mu times so it's proportional to V mu times the current of my new gauge group. But if this is not a conserved current in the standard model, for example, if it's not baryon number, if it's not lepton number, or the hypercharge, then it means that you have very strong constraint in the low energy theory. So it's a bit subtle, but quite easy. You just have to use the Goldstone equivalent theorem. With energy much above the mass of the bosons that you're looking at, the vector boson you're looking at, the longitudinal modes will actually participate into this process. So you can replace V by its longitudinal components like this. But if you take an integration by part, you see that basically this interaction here will increase as 1 over mv. So the smaller the mass of your vector particle, the stronger. Except it's, of course, this is a global symmetry, meaning that this vanishes altogether. But the problem is that, well, there is many interactions in the standard model which are not specifically a global current. You know, if you put any tree-level violation, you're done. If you put weak isospin violation, for instance, if you don't want to couple to neutrino to avoid some constraint, then they will also create this kind of interaction. As soon as you put an axial coupling interaction, then of course this is also broken, and the breaking of the Y identity becomes proportional to the mass of your fermions. So altogether, this is something that if you're, let's say, interested into a theory of Feebly interacting particle, which you want to couple, let's say, to. So if you're interested into a vector particle which couples to a current which is not conserved in the standard model, you have to be really careful that at low mass, you may have constraint which just blows up because of this dependence in the charges. Okay, so I think the last bit before we stop is just a word of caution. This will be my third. You have to also be careful about the radiative generation of the first generation couplings. After all, as I said, FIP particle will have a renormalization group evolution. And in many models, in fact, you're actually pretty interested into avoiding first generation couplings. This is because, as we're going to see in the next part of this talk, they are very constrained. And so it would make sense to use, for instance, an mu minus L2 model or some new interactions which would only talk to second and third generations. So it's much harder to get limits from those objects. So if you do that, however, you have to be careful because, well, generation might come back with by the back door. So if you remember what we discussed for the vector particle, the kinetic mixing terms, suppose that you put an L mu minus L tau vector boson, V mu, then you'll be able to create a loop like this. So you have a photon, then a loop of muon, and a loop of tau, and then your V mu. This means that the self-energy of the photon and of the V will pick an off-diagonal contribution, and that when you'll do the diagonalization, you'll need to rediagonalize these objects. Exactly like what we did for the case of the kinetic mixing. In fact, as I wrote to you before, this loop is kind of equivalent to having some coupling suppression times the loop factor and some log times here. So basically, even if you have a small interaction with the muons, or that you want this to be, let's say, 10 to the minus 1, you need to be careful because it will recreate via loop diagrams an interaction with electrons, which is, of course, only one loop suppression. So 10 to the minus 3, 10 to the minus 2. But because we have often very strong constraints on first generations, it may not always be enough, let's say, to escape limits. Of course, this is the case for a vector, but you could do the same for a pseudoscalar, and so on and so forth. Basically, you just have to be really careful that when you deal with very large coupling for a Feebly interacting particle, just because you go to second and third generation interactions, that the RGE evolution will just not recreate at the low energy scale the interaction that you try to cancel out. Okay, so I think, yes. So I suggest that we stop here for a short break, except, yeah. Sharam, is that fine?
Yeah, definitely we can take, 5-minute break.
Okay, so let me just look at the time now. Oops. 8:03. Let's come back at 3:10. Does that work for everyone?
Oh, I think it's perfect.
Okay. So for the one who are around still, we'll come back, let's say, at 3:15. And yep, okay. Since then, I mean, I'll be still around, so I'll just grab a coffee myself. So if you have any questions or that you think of something to ask, you can come back and ask in the meantime. Afterwards, just put it in the discussion, and then once I reconnect, I'll just ask it. Okay, so see you in less than 10 minutes then. Okay, so we are back. Let's wait a bit. Did everyone manage to get a coffee or a glass of water?
Yeah, you can start whenever you want.
Very good. Oh, what do we have? So, okay, I promised I'll do that thing in 2 hours for the first part, so we'll manage to stick in 2 hours. So, okay, let me jump back to that. First of all, I need to share my screen again. Okay, and I think I'm here now. Okay. Good. So for everyone, was there some questions in the beginning of the lecture before we go on? I mean, there is no stupid question, so no is a very good time. Yes, no, everything is understood. Okay, so very good. Because I still trust you, but not that much, I will nonetheless put a reminder of what we did before. So we spent an amazing hour so far trying to build models of particles. In the next amazing hour, we're going to try to construct a bit more models and look at some of the constraints that we could have on these particles. So, okay, the first thing we're going to look for is a dark photon. So a dark photon was this massive spin-1 particle. So if you remember, it was interacting with a standoff from this tiny interaction called kinetic mixing. So you see that here is my particle operator. So that was the vector particle F mu nu. So here is my new physics operator, V mu nu. And altogether, the main effect after you do not a rotation, but a transformation of the fields so that you diagonalize the kinetic term, you end up with this kind of interaction here, in which your dark photon picks up something proportional, so interactions proportional to the one of the photon. There is this tiny parameter here. So this V is a massive photon, basically. And the electromagnetic charge of every particle interacting with this object is suppressed by a tiny factor epsilon. So this is the name we go, this is why we basically call this guy dark photon in the first place. Okay, so we'll do a bit of pheno now. Now we want to ask this question, which is basically, how do we look for this object? So we'll do this very slowly, and really, again, please stop me if you have a question at any time while we derive all those limits here. So this is a very big plot in which I'm putting on the x-axis the mass of my object. So you see that I'm moving roughly all the way up to near the LHC, an object which has like the tens of GeV scale, all the way down to something around the MeV scale. So how can we look for certain objects? The first thing and the most basic way of looking for an object is as a resonance. After all, you can look to produce this particle in your collider. So you produce it at LHC. Then it will decay promptly because it's supermassive, and even if the coupling is a bit suppressed, it will still decay very fast. And so you just want to look for a resonance. So for instance, your LHCb, you have a huge subtle of dilepton final states, which are produced via this kind of production. So for instance, the V has been produced via beryllium, and you look for dilepton resonance. So you can do that in LHCb, you can do that at CMS. LHCb being more forward has a better resolution all the way down because it can look for objects with smaller PT. So you'll notice in that thing a very small bump there. Does someone knows actually why this bump is here? An idea? So this bump here, you see that it has a separation part there. So clearly it must come from a second types of signal, right? Because it's really not related to the previous one there. So this bump is from displaced vertex signature. So that's something that you've probably heard already, that LHC starts to be doing, that LHCb had been doing from sometimes by now, and which is extremely interesting. It basically tells you that, well, you could look at the LHC for particles which would nonetheless be just long-lived enough that they would go through your tracker undetected and then decay somewhere later on. I mean, the worst case scenario, they decay into your muon calorimeters, but before they can decay directly into the hadronic or the electromagnetic calorimeter. So this is what you see here in LHCb. So they look at the muon and they have this tiny bit where they were able to like be a bit better. And this were because they were looking at displaced dimuons. You'll notice the threshold of this production here, which is quite trivial. It's exactly at twice the mass of the muon. And this is because LHCb is much better at looking for dimuon than it is at looking for dielectrons. There are way more background in electrons. Okay.
And Luc,
oui?
Also you have some, on the top right, you have some sharp white bands that are crossing the...
Here?
Yeah.
Yeah. Very good question. So let's gather together what these limits could be. So 2, 3, 4, 5, 700 MeV. So Anno knows probably what is at 700 MeV around here. Those are the rho and the omega resonance. So you start having omega. And they decay also, leptonically, right? So if you have a V precisely there, the difficulty is that now you have like a peak, but how do you know that the peak comes from the V or comes from the rho? As a matter of fact, the two will start mixing a bit. And so instead of having a very nice narrow peak that you can see from the background, now you'll have one nice narrow peak, but maybe there are two in that guy. So it's significantly harder to see. And in fact, it's the same everywhere. So you see that this is the rho. And the omega, this is a phi resonance, much more broader, as you can see. Then you start entering the harmonia problems. So this is where 1, 2, 3, Jepsi. I don't know what is that for actually. Some excited Jepsi maybe. I mean, harmonia resonance is good here. And this one is U epsilon.
Okay, those are resonance.
So basically the problem is that if you really want to look at those objects, it's a bit hard because, well, there could be mixing with the hadronic vector mesons that we have. And it's pretty hard to see. It's not that it's impossible actually, because if they mix with the vector meson, they will maybe change a bit their properties. They may change their mass around. So you may put some limits, but it's not from a dilepton final state, basically.
Okay, thanks.
Okay, so now you're very welcome. So in fact, you can do the same thing from a different approach. And this different approach is the plus E minus collider. So here you see that you have a bit of a different approach again, because instead of producing it directly via Drellion, you said, okay, I have access to somehow lower, because I mean, you could do that at LHC, because LHC is a PP machine. And so therefore you have a form factor on the energy of your particles. So even if you're at 13 TeV center of mass in practice, the LHC, because it's a proton-proton and you have to extract something from the proton, you're scanning smoothly around the entire mass range from basically 100 of GeV all the way up to 13 TeV. Of course, that's something you cannot do if you have access to any plus minus machine, because here you're really on your, you're exactly on the center of mass energy of your two particles. So the second way of looking at it, if you have access to E plus E minus colliders, is to look for what is called associated productions. So in that case, basically you are E plus E minus, then you go to a dark photon and a photon. So there's two things, something that you can look for in a pretty large range of machines, from Chloe, Bell 3, Babar, and in the future Bell 2. So you see here the strategy is a bit different. You look for both these dilepton final states and a photon. And so this photon has to be visible so that basically you can reconstruct the complete energy of your particles. You require both high energy photons and that you reconstruct these two bump into your dilepton spectrum. So this allows you basically to reduce the background quite a lot, and also allows you to go to particles which are significantly less massive, and therefore have a lower, transmit lower PT, so that it's a bit harder to distinguish the dilepton finite state from the background. So you see this covers all the way HIP. In particular, you see that you have a sharp cutoff there, somewhere around 10 GeV, and this is simply because Babar, which was the highest energetic object that we had available for E plus E minus colliders, stopped at 10 GeV of center of mass energy. So now you have to keep in mind that this will also have projects in the future for displaced vertices signature. So we may have the possibility of probing a bit down, either by accumulating more statistics or by looking at displaced vertices again. Okay, so that was like the most simple way you can think of, basically, of looking at these types of objects in the lab. Just look for a bump in a dilepton spectrum. So to go forward and actually probe, we'll have to get a bit creative. Be creative means basically using mesons. So the point is that as soon as you have a particle which gets to be significantly lighter than, for instance, the pion or the eta mesons, then you start having an extremely effective way of producing it via the decay of mesons. So we'll come back to this production cross-section later on. That the pion decay is mostly into two photons, 100% in fact. And now we have an object which behaves exactly like a photon, but a tiny suppressed coupling. So in fact, the pi zero can also decay into those objects. So then we have several ways of looking at this thing. The dominant idea is to turn toward mesons factories, which are basically shooting proton on a target and having a high intensity meson beams of kaons, for instance, if you're at Na62, or pions if you were at Na48. No, sorry, Na48 was also kaons. But depending on where you were, you could look at this light lepton, light mesons, so pi zero, k0, and so on and so forth. Then you wait for them to decay, and they will decay into one standard particle and a Feebly interacting particle. So then either you see this object, or you don't see it, and you just trigger on the missing energy. So for instance, NAC looked for pi zero with a photon, so decay into one photon that they could trigger on, and then a V decay into E plus E minus that they could also trigger on. So you see that this enables them to probe even more this regime here, and you see that the cutoff is precisely at the pi zero mass. So the first strategy you can look for. Then you can also try to look at something a bit different to try to say, okay, even if I don't see the decay of my particle, maybe I can still say something. So you can look for missing energy. And there you can have this kind of limits here, which comes from Na64. Basically, they say, okay, we're in a situation where we're going to produce these objects, but it's so light in mass, so basically below, let's say, 20, 30 MeV, then it's going to be stable with the boost factor that I'm producing in my detector. So Na64 shoots a beam of E plus E minus on an active target, and they measure very precisely the energy. So they know that as an entry energy, they have 150 GeV. And if in their entire target, they have less than, let's say, 50 GeV of energy, they trigger and say, oh, I have 100 GeV of missing energy, that cannot be. This could not escape my detector. So it must be that I have produced a light object which escaped it. So of course, this strategy works very well at low energies, but you see that it stops somewhere around here, and it stopped, of course, because at one point, this particle that you're producing will just decay again in your target, and so therefore there is no missing energy, because if you produce the particle and it redecay instantaneously, well, the detector will still see all of the energy of the event, basically. So this is the reason that we have that right here. Interesting sets of experiments that we want to look for is what are generally called beam dump experiments. So we'll spend a bit more time in the rest of this presentation on that, because I just want you to understand a bit why we have this very peculiar shape there. So you see that those are completely different from the other ones. So the other ones were quite logical, right? Like were used at LHC. You have a mass, sometimes you have some thresholds, and then basically the couplings, you can go down in coupling as good, as good as you can. And at one point you stop producing this particle, you stop seeing it on top of the background, and then it's finished. Meet anymore. Those are completely different. You see that they have both an upper limit and a lower limit. So the way they work is the following, and we'll spend a bit more time back on the paperboard trying to actually see why we have this peculiar shape there. The reason is this search is there, compared and distinctly from this Na64 one, requires what is called a visible signal. So they want to see something in their detector. So the way they do that is by having a beam dump scenario again. So here the idea is that you're going to take a proton beam, and you want this proton beam to be as energetic and high intensity as possible. I mean, we're talking 10 to the 22 proton on target. Those are crazily large numbers. Of course, there's a proton beam, so it's an extremely also background. You have a lot of background in an environment. So what you do is that you said, okay, no problem. I'm putting a shielding here. This could be like earth, rocks, active shieldings, lead, and I'm putting 100 meters of it, for instance. After this 100 meters, I'm absolutely sure that there is no anomalous particle which remains. So we'll come back to that a bit in a second here. My detector here. So there is no anomalous particle which can replicate that, and we'll again come back to this part. And what that means is that you're operating basically in a background-free environment. Of course, there will be two limits here. The first lower limit occurs when you stop producing this particle. This is a lower limit. And the upper limit will be when the particle decays too promptly. So basically, it does not have the time to go through the entire shielding. On the other hand, it will decay in the shielding and therefore leave no signal. So, okay, you can do the same from proton, and you can also do it for E plus E minus, which finish covering up this entire business there. So you see that all together, and just focusing on a pretty narrow range of mass compared to what I showed you before, which is MeV to tens of GeV, we're able to use an entire diverse set of experiments, pretty much any existing or which has existed accelerator experiments, in fact, has something to say one way or the other. So, I mean, we can start from CMS, which is at HCB. We had LEB, we had Chloe, the colliders at Interascati, and so on and so forth. So basically, any experiments available at one point basically gave a limit on this dark photon, which makes it a pretty amazing summary of the entire sets of particle physics accelerator business since, let's say, the 1960s, 1970s, like E137, for instance. Okay, so let's finish that by doing a bit. Yes.
So the picture you were showing us, all the constraints they come only in the case where you have a vector portal, or it's whatever Feebly interacting particle.
So each Feebly interacting particle has a somehow different phenomenology, but it can be basically linked to two different parts: the production mechanisms and its decay length. So basically, this is what you'll get for a dark photon. But if I had to give you the limits for an axion-like particle, for instance, that would be almost similar. I mean, it will have the same shape. You'll have accelerators here. You'll have some displaced vertices signal there. So okay. It's always like that. If you the only thing we change is the ratio between the production and the lifetime. So if you look at heavy neutral lepton, it's also the same thing. You'll have like fast decay and displaced decay. But this blob here can move more or less up or down. So in certain cases, there is no gaps, simply because you're always in a regime where if you can produce a particle, you can see it. And in other cases, you have even a larger gap than that, which is, for instance, the case for an axion-like particle, which couples two electrons, for instance. They have typically a longer lifetime, so it's even harder to, a shorter lifetime, sorry. So it's even harder to see them in this kind of experiment. But in practice, yes, what I showed you here is a pretty good summary of like the types of constraint you should expect. You have some missing energy searches here, some visible searches, prompt decay, some display signal, which are called to be much more in the future, fortunately, and some long-lived particle range.
What is your feeling about those constraints? I mean, for me, it seems that there is still plenty of room to.
Oh, there are. I mean, this is why like these are just like existing experiments. This entire regime is supposed to be probed in the next 10 years-ish, all the way down here, mostly.
Okay, great.
So, I mean, to know exactly like what will be done, what will be built or not, another question. But you have to keep in mind what is amazing about this part of the parameter space is that you don't require a very large machine to look for those objects. So, because you see here we are like what, 0.1 GeV? It's extremely easy to construct an accelerator which has the energy of producing this particle. So the challenge is to have the detector which could actually see something which decay a bit fast, but not too fast. So there are ideas to do that, for instance, or simply ideas to say, well, look, I can just increase the intensity of my detector so that I would go down here. And there's also another possibility, because in fact, a significant part of all those constraints come from all dish detectors. And so we have facilities coming, hopefully pretty soon, which would have access to significantly more proton on target, like 10 to the 23, or way more electrons, because they would just ramp up the intensity. And so that would enable you just to go down, like statistically. We have also to include that Babar here. So now we have already Bell2 running. So anything that Babar could do, Bell2 could do it again, but with what, 100 times more statistics eventually? 10 times, I think at least 10 times. So that means that you will be able to take this epsilon and put it down at least there, just from Bell2. And this is something that we're expecting relatively soonish, because basically we just need Bell2 is already, I think, accumulating as much data as Babar, if I'm not mistaken. So in practice, you just need to wait a bit more. I know the instantaneous luminosity that they have is higher than Babar. And the analysis is relatively simple, because you just want to look for monophoton plus a pair of objects. So it's pretty simple analysis to do in your data set. So in practice, that would mean that this would like help cut this place down. But I mean, altogether, the good, it does not help to be extremely focused, let's say, specifically on this example here, even if it's the dark photon, so basically like the golden description of what could be a Feebly interacting particle. So of course, like most experimental collaboration aims at closing these gaps. But in practice, as I said, every Feebly interacting particle will tend to have this kind of shapes of limits when you look in this regime here. So even if an experiment could not probe new parameter for the dark photon, it's very plausible that it can actually do so for another Feebly interacting particle.
Great, thanks.
You're very welcome. So where are we now? Yes, so the last thing I wanted to do, as I said, is to come back for a second to actually writing things. Zoop. And what we will try to do is estimate a long-lived search. So I think it's all that we'll have the time to do, probably in the future, before we finish this presentation. So basically, what do we have? We had these very strange limits here, which go down there. So my goal here is to try to give you a small understanding of why you have this kind of shape and why we are in this regime there. So as you can see, I mean, this will be like relatively simple pheno, but quite illuminating, I hope, on actually how you can do something. So we are interested here into like long-lived. Okay. The first thing is, what do we mean by long-lived, right? So for that, we need to estimate what is the typical propagation length of a particle which is produced at a given boost factor. So typically, we're interested into Lx, let's say, which is typically given by tau x, the lifetime of the particle, times c, because those particles are all produced relativistically. Now this is given by an h-bar factor. Then you have to divide by the width of the particle, and then you have the boost factor and times c. So just to give you an idea on the orders of magnitude involved here, so this is just the reduced Planck constant, so 10 to the minus 25 GeV per second. And this is, of course, the decay width in GeV. And this is a boost factor of my particle, so we call it gamma x, and basically it's proportional, it's almost equal to the energy of your particle divided by mx. So if you have access to a machine which has 100 GeV objects, this will be 100 GeV divided by the mass of your particle. So you see that this can be quite big. I mean, it's important not to forget it, because if you are at 100 GeV beam dump experiments, for instance, you end up transmitting almost 100 GeV of energy to the particle you're producing, which can be super light. So we're talking boost factors of the order of 10 to the 4, 10 to the 5. So this will really be an important factor in what will be the effective decay length of your particle. So once you get this first thing right, this is basically what we call. So of course, what we want is to have Lx significantly larger than the length of the beam dump itself. Okay, yes, so we want this. So why is this a good idea, looking for that thing? Looking for displaced vertices with a particle which is a very long-lived thing. So the key idea is that, as I advertised to you a bit before, there is simply no particle in the standard model which would actually behave like this in the standard model, which would be both, in a way, which is both unstable, meaning that it's going to decay after a certain time, and not interacting with matter. So why is it so? Well, it's quite simple to actually see. from the list of particles which don't interact much. So what do we have? We can look, for instance, at the muon. It's long-lived, okay, that filled these bills. I mean, we know that muon can penetrate, but it's also charged. So even if muons are very penetrating, they will not, in practically all the time, go through 100 meters of rocks. No chance. It can go through the atmosphere, yes, but once you're 100 meters of rocks, you decrease your flux dramatically. You can have also neutrons. Those are neutral. They are super long-lived, but they also interact via the nuclear interactions. So neutrons are also quite penetrating, but not that much as to cross, let's say, hundreds of meters of rocks. And then the last bits that we can construct, of course, are neutrinos. Those are not very well interacting. We know that they can, without any issue, cross hundreds of meters of rocks. But they're also stable, meaning that if you want to see something from a neutrino, you'll need some matter for the neutrino to interact with. It will not like decay spontaneously in the vacuum. Yes, but they are stable. Stable. So basically that means that if you have an experiment which do something like that, right? So you have some beam here. So this could be a beam dump. This could be, I don't know, the LHC interaction point at Atlas, for instance. And then if you follow the strategy that I told you before, meaning that you put a FIPs here, which cross a very big shielding, at that stage, the only thing which will get through at the same time with this feebly interacting particle, which start from there, up and get through, are neutrinos. So we'll have both the FIP and the neutrino, which would produce and go all the way into a detector here. If instead of having an active detector like a neutrino experiment, you put something which is just a decay volume, so you completely empty a part of space, then what will happen? Well, they will never interact because there is nothing for them to interact with. But the feebly interacting particle, well, let's say in a pair of E plus E minus here. So if you actually put a detector here, let's say, oops, so this is, for instance, the scintillator, then search for the decay of something occurring where nothing should occur. And neutrinos should not interact neither. So basically, this strategy here, zero background experiment, which is of course extremely good to look for objects with a very high precision. So what these experiments could see? Well, this depends on two things, right? The productions and the decay rates of the particles. So let's start a bit by the production and focus on maybe the simplest case that we're looking for, which was the dark photon, right? So let's study the long-lived dark photon. The long-lived dark photon. So this long-lived dark photon, we know that the interaction Lagrangian, I've written to it several times already for you, it contains in particular interactions with, let's say, all the quarks. In particular, it has this kind of interaction. So it interacts with the up quark and the down quark, like this, times V mu. Of course, those are quarks, and we're in the very light regime. So yet again, we cannot describe something by the quarks. We have to describe it. Make a bit of a calculation, in fact, studying the chiral anomaly. So that what you'll get from these things is that the dark photon will also interact with pions. So this creates an effective interaction with pions. Interactions with pi zeros. So there is in fact an extremely simple way of knowing what will be, let's say, the branching ratio of a pion going into dark photon is just to remind ourselves that, well, main decay of a pion is into 2 photons, and this is near 100% branching ratio. But remember, this dark photon is basically the same interaction as a photon, just with the mass. So in the limit in which, let's say, MV is much smaller than M pi, 0, the pion doesn't see any difference between the photon and the dark photon. So it will have an interaction in which it may also decay into both a photon and a dark photon. And this will occur, proportional to basically epsilon square. Because remember, this tiny interaction here was suppressed by epsilon compared to the electromagnetic one. So this is the same as, so now we know that if we put a dark photon, epsilon squared times a pi zero will have a chance of converting not into a pair of photons, but into a photon and a dark photon. But we have pi zeros around. I mean, at those experiments, if you think we had like some pi zeros were in the 10 to the 18, 10 to the 19 range. So that means that we expect to produce many such dark photons. Oops. So the number of dark photons that we produce, this is what? Well, this is simply the branching ratio of pi zero going into gamma v times the number of pi zero that we have per proton on target, and times the total number of POT. Okay, so if we're actually at charm, so let's study the charm experiment, which is exactly what I showed you before. Oops. So this diagram here, this was what is called the CERN, Hamburg, what was the last one? Amsterdam, Roma, and the last one in FAG experiments. And this was exactly this kind of scenario. So you were hitting with the proton beam at the SPS with 400 GeV, the copper target, and they had a decay volume hundreds of meters away. And they had also 10 to the 18 proton on target was equal to 10 to the 18. So a huge number of protons at 400 GeV of energy. So basically what you get now is that then NV is, let's say, around 10 to the 6 times, I don't know, 10 to the minus 6 epsilon over square. So you see that even if we take a particle, which is 1,000,000 times less interacting than a photon, we'll still end up producing 1,000,000 of those objects in the charm beam dumps. So this is a crazy number. It's an extremely effective way of producing those particles. And I mean, the question is, okay, I mean, these are really a lot of objects. It's a huge signal. So how can I look for this signal? So the main question is, are those dark photons actually reaching the detector? Because as we've seen, to be actually detectable, you have them to go through the shielding and then decay in the detector. So to do that, you have to know the decay width of a dark photon. So basically, you have to look at these processes here, V2E plus E minus. So this is extremely easy to calculate altogether. I mean, I can just give you it right now. We'll do enough interactions. We'll do enough calculation of cross-section, I think, afterwards. Oops. So what do we get? The decay width of this object is what? It's proportional to alpha electromagnetism. It has to, right? Because this interaction here is E times epsilon. Okay, then there is a factor of 3 from the spin, and then you have the mass of the object itself, which decays. So far, so good. So if you plug everything together, you can bring this width into the expression I wrote to you before for the decay length. And then what you get is this, right? LV is something of the order of 1 kilometer. So you have to beat some conversion factor. Let's say I'm including the fact that the V has a boost factor of the regime of like 100. And this is for 10 to the minus 6 squared and an object which is at 0.1 GeV. Okay. So what do we learn? We learn that if we have at charm a particle which couples 1,000,000 times less than the photon, we're going to produce 1,000,000 of those particles, and their typical propagation length will be of the order of the kilometer. So remember that charm has a shielding of the order of the 100 of meters. So how do we know how many particle decays? So the last bits that we have to know is like how many dark photon will now decay in the detector. So this is just a simple probability estimate, but one has to be a bit careful sometimes. Okay, so the probability of the decay is what? Now we have a particle with a given width and a lifetime, and so it's an exponential decay loss, which has no memory. So the first thing we need to take is to say, well, okay, I want the particle to survive, because I don't want it to decay in the shielding. So it has to the detector distance. So let's see if we come back to these small things here. Yes. this distance here is d, and this distance here is L. So we have the distance of the detector to the interaction points. Okay, so the first thing we want is that we don't want this particle to decay, well, before it actually reach my detector. So that's very easy because I know the propagation length of this particle, so it's just the exponential divided by the two things. Then once they actually reach the detector, well, I want to see them, right? So I want them to actually decay in my detector volume. So basically it means that we have to ask that then it decays 1 minus the probability that it does not decay into my detector. So this is quite simple. You see that it's like probability of survival, and then signal. If you want to be fully consistent, you have to take into account that, well, you may not be fully collimated, so you may have some geometric acceptance for actually reaching the detector in the first place. So what do we know from that? Well, there is many regimes which are interesting here, right? So let's look a bit of the different regimes which are available. The first one is that the particle has a lifetime much longer than the distance of the detector. So this is basically what I would call the quasi-stable regime. Basically, the particle will escape, and then you have a small chance that they actually decay into your detector. So in this regime, what do we have? Well, this first term here will be roughly 1, because by definition, the lifetime is super long, so the term, the exponential, is 0. The second term we can expand, because L is typically smaller, so the size of the detector is smaller than the distance to the interaction points. And so therefore, it gives us something like L divided by LV, which is much smaller than 1. So this is like the quasi-stable long lifetime limit. So you see that in this regime, what do we have? We have a 100% chance of survival. The heartbeat is that most of the time the particle will not decay into your detector. Then you have another regime where LV is much smaller than D, and this is the unstable regime. So then what do we get? Well, this part here is extremely small because it's exactly an exponential, so much smaller than 1. On the other hand, once you actually reach the detector, you're just certain that it will decay into it, mostly. So this is somehow smaller than 1, but closer to 1. Of course, it does not really matter here because you see that we have an exponential suppression in front of this guy. So if your particles survive all the way to the detector, then okay, you're done. You have order 1 probability that it decays. So you see that this is extremely hard to go forward. But this one is just a suppression in 1 over LV. Meanwhile, this one is an exponential here. So basically, once you reach the point when it starts to get short-lived, it will exponentially vanish. So it will be extremely hard to see this particle by just adding more statistics. What you need is an experiment which is just closer or which has a larger boost factor. The last bit, which is of course the most interesting one, is the place when basically you have both LV of the order of the distance. What do we have here? Well, we have both factors of order 1, right? The exponential is of order 1, and the signal, if L is of the order of D, which is typically most of the time the case, is also of order 1. So in a situation where basically instead of having a very strong suppression, every single dark photon that I'm producing up to an order 1 factor will decay in my detector. And remember, we're talking about millions of particles here. Typically, it means that this type of experiment is sensitive to the region where you have exactly LV of the order of D. What does that mean? Well, we can just take back what has LV before. Oops. So we see that we had this discrepancy here as function of the kilometer, gamma V, and everything. So we can just reconfine this one here. And basically, it means that this will give us a relationship between, let's say, 1 over mv epsilon square equal a constant. So this epsilon square comes and mv comes from the production only, which means that basically this golden regime where we'll be able to like see all the time a particle, basically, will follow something like epsilon proportional, will follow proportional to 1 over square root of mv. And if you're in log scale, this is the case here. Oops. If you're in log scale there, you'll have minus 1/2 as a dependency of epsilon as function of mv. And this more get as these types of golden ratio. This, of course, stops when these two regimes, the quasi-stable and the unstable one, match one to the other, meaning that in one part, at one point, you'll make the particle more and more massive. And then at one point there, you will just not be able to produce it anymore. So it will stop. And on the other hand, you see that here the dependence is a bit different because it's just about the particle being unstable. And then at one point, you increase the mass, and this particle starts getting more and more unstable, and it crosses again. So basically, these two shapes cross, and this tells you where you stop. Of course, like smoothly describing what happens near the tip is quite hard because it's very hard to describe from a Monte Carlo approach what happens there. You have particles which, like billions of times, do not decay, but you produce a lot of those objects also at the same time. So it's a pretty hard regime to simulate properly. Okay, so altogether, this is the next bits. Okay, if you're really interested, you could also, in fact, use these types of approach to also get the full number of signal in the charm experiment, and this gives you something like epsilon geometric, which is of the order 10 to the minus 1 in charm, times 5 times something like 500 gamma v, times epsilon over 10 to the minus 7 divided by 4. This is the long-lived regime. This basically gives you this low part here of the spectrum in this place there. But you see that this is rather amazing, I would say, to think that using this kind of techniques, and charm is an experiment which stopped working before I think I was born, but almost. And still, this can give you a constraint on a new particle beyond the standard model, which couples 10 to the minus 7 times less to matter than the photon. This is absolutely nothing. Yet we still have the possibility of look for this simply because, well, we pay a very small price at the production. And when you're in the good regime, almost 100% of your particle ends up decaying into your experiment. Not 100%, of course, but like order 1. And so this means that you're extremely effective at detecting this object once it's produced. And because you produce a lot of them, well, you get a strong constraint in these types of objects. Okay, so I think we're nearing the end of this lecture there. So, okay, I think I left for the next time a discussion about, that I'll do very briefly about the flavor aspects of Feebly Interacting Particle. And I think I'll just stop here for this first lecture. Okay, do you have any questions with respect to these things?
I will let the other if they have any question. Else I have one. Now if someone else has a question. Don't hesitate. I will start. So the D that you are showing us is the distance, the value D that you are comparing.
Oh, yes, on this one. So let me come back there. Yes. This one, yes. Mm-hmm.
So that's the distance with the detector.
That's the distance between the production of your dark photons, so the beam dump itself, and where you can hope to detect them, which is the detector. Between those two guys, you have the shielding.
But the production, the place where the production happens, you more or less control.
Okay, let me just put my here. The place when the production happens, yes, is more or less controlled because typically, we're here. Most of the production will occurs within, these are typically copper targets for charm, for instance. So the radiation length and the hadronic length of those objects are of these tens of centimeters, more or less. So they use like a meter size target. And then you have 100 meters of shielding and another one in the detector. So you can basically approximate the target as being like 1 point. And then also like just the distance from this target.
But then the detector is very large to be able to feel this specific regime, or can you move the detector to feel it? Because you need to be at the right spot.
So exactly. You can in principle try to move your detectors around, but there is a difficulty. So in fact, if you see all of those limits here, you see that they kind of vary a bit widely around, like certain of those are like significantly better. And this is not really because they did the experiment better, just because they had different parameters of inputs, like ARM, for instance, 137 were like high energetic experiments pretty far away, but using huge statistics. So this enables like to go very down there, but not very good here. So in fact, the lower the energy of your beam, the lower is the boost factor. In that thing here. Yes, you see from the relationship that depends where you want to go. If you want to go down, it means that you have to get this lambda as small as possible, right? because you don't want a particle to be too long-lived. There is a suppression factor, which is given by this here. So if you want to go down, you need a particle with as many particles as you can, a bit far away, but okay, you don't care. You're in the very long-lived regime. So the detector has to be as big as possible. You don't care the distance, it has to be big. And you need this gamma factor to be small. And in this way, you can go really low. If on the contrary, you start to probe this regime here, then it's completely different, right? Now you're in a situation where your particles tend to decay way too much, but you're also producing a lot of those. I mean, if we were to take our numbers here, 10 to the 6, 10 to the minus 6, I'm at like, I don't know, something like 10 to the 5 there. You're producing billions of those objects, literally. So the production are huge. The main issue is that none of those will actually be able to reach your detector, and they're completely swamped by the standard model background in the shower. So what you can do is try to either increase a factor. So this is why like some of the dominant constraints here come from high energetic experiments like NuCal, for instance. And you want these experiments to be as close as possible. So then what will happen? Currently in the future, I don't think I have some projections there. Yeah. So in the future, what will happen now is that either we'll go down by selector searches, or we'll try to get better boost factor. There is a place when we could get boost factors much larger, and this place is LHC. So in principle, you can very well look for a signal like this one. Oops, sorry, there. One more. Yes. So instead of looking at the beam done experiment here, you look at an LHC interaction point. So the Atlas interaction point, for instance. So you lose a bit in number of pi0 produced, for instance. But on the other hand, light particle LHC are produced extremely forward. So now this is your LHC, and you're going almost in the direction of the beam line, but not exactly. And then you put yourself 200 meters away in the beam line direction. And this proposal is called phasor. And okay, you have others, but those are more or less the same idea. So 100 meters into the direction, you're going to catch the pi0 produced by the primary vertex pi of the LHC produced at the TV. That means that the boost factor, you'll gain a factor typically 10 to the 1, 10 to the 2. So typically it means that you then look back at this expression here. Yes, instead of having a typical lifetime at the minus 6 of the kilometer, you'll be at 100 kilometers. So of course, you're interested into the other regime, right? You want to get epsilon small, so you can get it to 10 to the minus 4, for instance. So this lifetime will be of the order of 10 meters or something, 100 of meters. And so you'll use your huge boost factor so that you are able to probe, make this particle live longer, basically. The other possibility is to try to put your experiments as close as possible to the detector. But at one point, you cannot do that anymore because, well, if you're using a beam dome experiment, you need some length of material to stop all the particles, right?
Yeah.
As I said, muons are quite penetrating, especially at 1 GeV, or hundreds of GeV, as are muons, in fact. So you just want to make sure that you're really stopping all of those particles precisely. And the more you get closer, the more background you start producing. And then you start losing by insensitivity, because those searches are all like 0 background sensitivity search, so 3 events, basically. The last option, which is the one taken by LHCb, is to look at displaced vertices. So there the idea is that you could look for something like a centimeter lifetime, and you'll have less statistics, but on the other time, because you're within a very big detector, you control everything. So you don't have that much background because you're really able to pinpoint very precisely what happened, something which vanished and something which reappeared afterwards.
You can reduce the background. Okay.
And that's why you can reduce the backgrounds, because for instance, there will not be much background which would say, you know, have a pi0 decaying with like 1 monophoton interaction, then suddenly after 1 centimeter of pair of E plus E minus. There will be some, but not many. And if you really control everything in your detector and are able to reconstruct the mass of all the objects, then you can try to go forward and bridge it. So there are proposals here, and I also hope that they will be done. I mean, there was a good proposal at Bell 2, for instance, which could have been able in one shot to completely close this part of the parameter space. The problem is that it's not been done so far. So it's still unclear whether or not, like experimentally, like they would control enough the detector to do it, and be sure that, you know, it was not just like lost in one part of the supporting structure, for instance.
Okay, but you have good hopes that it's going to be done?
Yes, I mean, this part will be closed in the near future. I mean, let me just... Okay, this is like maybe a bit old, but let's look at Feebly Collider. Why I cannot connect to it? Okay. Can you still see my screen?
Yeah.
Okay. Okay, this is a good source. Now it will be replaced probably by some white paper. US community, but okay. This was the one from Physics Beyond Colliders. Oops. So let's see. This is a minimal dark photon mode. This is more or less what I showed you before.
I see. I recognize.
Part of what I showed you before is here, so you see that you could have still some of this. Oops. So you have plenty of things together, but basically this green line is LHCb as displaced vertices searches. This is BEL2. You have also BEL2 searches in displaced vertex mode, which are not represented, which we'll cut there. Sequest here is a proposal to get a near detector with more or less just more energy. So basically here you try to get beta boost factor and closer detector and strong statistics. And then, okay, you have different proposals like HPS, which would probably not arise, but also PADME, which is not written there, which would be able just to get better at the accelerator search. But I mean, if you put everything together between phaser, those objects and everything, this will, at least this part all the way up to 200 MeV should probably be crossed in the next decade. So yeah, at least from this part, there is very good prospect that it would work, and also like good pheno to be done in the meantime. And while looking for this kind of objects, yes.
Thanks.
No, you're welcome.
Is there any question?
Are there any other question on this? Yes. Come back to that. Okay.
I think yes.
That was super clear. That's very nice. Anyway, so okay, this is very good. So we went most of what I wanted to do for that. So I've seen we've covered this lecture basically all the way from some very basic theory things. I hope it was not a bit too basic, but it's always useful to actually write it down at the Lagrangian level how you can create this kind of object. Then this is the most basic also pheno that you can look for, like how can you constrain and test this kind of object. So the plan is like in the next lecture that I very strongly invite you to come to, which will occur next Friday at 2 p.m. We'll look into a bit more of the actual pheno of that. So if you actually knew what I presented today, because you already knew about this Feebly Interacting Particle, then Friday you'll learn hopefully a bit more, because this will be more about really some actual pheno. So I'll cover everything regarding dark matter. So in principle, like why this kind of objects were pushed forward first for models of like dark matters, and they have very strong link with dark matter. So that's something that is important to discuss. And then we'll discuss very briefly the flavor connection of this kind of structures, because so far I've strongly advertised to you that this kind of objects, well, you could not really just stick to the portal operator that you've written at the electroweak scale. You need to be careful. You have Riemann group evolutions. So you have also the possibility that those objects will feel flavor to a certain extent. So we'll see how we can build objects from that. And finally, we'll touch a bit briefly, depending on how much time we have, on some anomalies. And in particular, this is extremely important to look for, let's say, to look for the g-2 anomalies. And depending on time, we'll look a bit on more exotic stuff like the X17. But I think this is a bit ambitious in 2 hours, so we'll probably stop somewhere in the middle there. Okay, so in the meantime, thanks a lot for coming. And we see each other on Friday, I believe.
See you on Friday. Thanks a lot. Thanks.
Ciao.